Hello everyone, this is lecture 13 of PEC. Let's discuss the balanced bridge. In the previous lecture 12, we introduced the serial, parallel, and serial parallel connections of resistors, but unfortunately, not all connections of the resistors are serial parallel connections. For instance, this circuit is called a bridge. Based on the original parallel connection of these two series resistors and other two series resistors, there is a branch as a bridge connecting these two branches. So it is called a bridge. Because of the bridge, there might have relationship between these two branches. So the relationships of these five resistors are no longer simple serial parallel connections. This certainly brings trouble for our circuit analysis, but we will introduce later that the bridge circuit is very useful for the applications. This lecture will introduce a special situation, that is, the balanced bridge. We can transfer a bridge circuit into a serial parallel circuit. In the next lecture, we will discuss a general solution, that is, to transfer any bridge circuit into a serial parallel one. Okay, we start to deduce. Assuming that the bridge does not exist, we set this node as a reference point. We can draw the reference point like this. Also be like this. These two ways are equivalent. According to the reference points, also based on the last lecture, in which we discuss a voltage divider with two series resistors, we know that UA is equal to R2 over R1 plus R2 then times US. We also know that UB is equal to R4 over R3 plus R4 then times US. We need to discuss a special case, that is, R1 times R4 equals R2 times R3. What's the relationship of UA and UB in this case? Let's deduce it. R2, R3 is divided by R4, then substitute it into the equation. Cancellation, cancellation, cancellation. So it is equal to UB. We see that UA is equal to UB when in such a special condition. If the open circuit voltage of the two nodes are equal in the circuit, we call these two nodes the equipotential points. There is a very important conclusion in the circuit, that is, when we use any resistor to connect the equipotential points, it won't change other branch variables. That means between the two equipotential points, it can be open circuit, that is now infinite resistance, short circuit, zero resistance, or any resistor. There isn't any change for other branch variables in this condition. How can this conclusion help us simplify the analysis of the balanced bridge? Look at this circuit. It is a bridge in the first place. Secondly, because 1 times 4 equals 2 times 2. It is a balanced bridge. So for this resistor, we can change it into an open circuit or a short circuit. It has no effect for I2, I5, I6, I3, and I1. So if it is open circuit, the circuit is a parallel connection of the 1 and 2 in series and the 2 and 4 in series. If it is a short circuit, the circuit is a series of the 1 and 2 in parallel and 2 and 4 in parallel. You can analyze that the results are all 2 ohms. So the circuit becomes very simple. We can analyze and solve I1 to I6. by using the conclusions of the serial-parent connection discussed in the previous lecture. It should be pointed out that because this is a balanced bridge, for any resistance on the bridge, there is no current flowing through it. Therefore, I4 is always equal to 0. We can use this to do a very meaningful thing, that is to detect resistance value. We draw the circuit here. We change the bridge resistor into a current meter in the circuit. This is a resistor whose resistance needs to be measured. Other R1 and R2 are known value. We can adjust the value of R3. This is a variable resistor. According to the previous discussion, we know that when R2 times R3 is equal to R1 times Rx, the current of this bridge is 0. So we can observe the reading of the ammeter while adjusting the value of R3. When it meets this condition, the reading of the ammeter is 0. So we can know Rx is equal to R2 times R3 over R1. This is a bridge which is very important for the measurement of the resistance. Okay, that is the end of this lecture.